Hello, everyone, and welcome to another episode of the GC 100 podcast. I'm your instructor and host, Dr. VG. All right, today we have an exciting lecture for you filled with many animations, literally, where we'll be examining air masses and weather systems. So let's begin. So let's just kind of begin with our understanding or appreciate what air masses are. And then as we understand air masses, then we'll further kind of apply this to understanding a mid-latitude wave cyclone. We'll think about the anatomy of a thunderstorm, and we'll think about the recipe, so to speak, for tropical cyclones and hurricanes. So what is this term air mass in this context of weather, climate, and meteorology? And so an air mass is a large body of the lower atmosphere with the uniform conditions of temperature and moisture. What that means in so many words is we're thinking about a large, like continental to subcontinental scale mass of air with relatively uniform conditions. It's about as cold and has is dry or moist. And so in this way, really for us in the continental US and then here across North America, we can think about major air masses. And really on this map exists the major air masses that can influence us here in the mid latitudes. And so when it's really cold in the winter or cooler than normal in the summer, we're often being affected by Arctic and continental polar air masses that originate way up in the Arctic and come all the way across and or originate in these polar continental regions. And so here, this is this relatively uniform mass of cold or cooler air. And when those air masses descend across the continent, moving from north to south, we're thinking that here, at least us in the Great Lakes, being affected by those continental polar air masses. And not to go through all of them, but appreciate that our air masses are largely subdivided into two major categories based upon moisture content. And so that would be continental, as we've practiced before, or maritime. So did it originate in a continental location or did it originate in a maritime location, meaning there's much more moisture due to evaporation? And then it's further classified based upon relative latitude. And so if that air mass originated near the Arctic Circle, literally we'll call that an Arctic air mass. If then it was a little bit further south than the Arctic Circle, if the air mass literally originated further north than us, or that, but also further south than the Arctic Circle, we'll say that's a polar air mass. And then here, air masses originating from our south are tropical. And so really the air masses then being Arctic, and then here polar, and then here tropical. One thing that we'll really focus on as we come through or work our way through this lecture is really almost always, or at least within a scope of like days or a week, typically in the Midwest or most of the US, there's at least two of these air masses interacting with one another, and maybe even multiple, like three or more. And so often that could look like those air masses colliding or converging. It could kind of look at them like deflecting. It could look like one being having more energy and motion and like literally kind of just pushing another one. But anytime these air masses interact, there likely is a front or a boundary that's separating the two. And that's largely what we'll kind of continue to focus on here. And so one thing I wanted to do is kind of and just provide this animation I found from University of Colorado, showing some time-lapse imagery from a satellite of an Arctic air mass that was really kind of originating up here somewhere. And you can really just see kind of based upon the clouds, but you can see that air mass descending over the Great Lakes. And then to tie in some previous lecture content, that would be when our lake effect snow system would ramp up if it was in the winter. And so to kind of provide some context of an Arctic air mass moving from north to south, this is what it would look like from space. So let's check it out. So you can kind of see this Arctic air mass coming all the way down and across, and it's a short animation. We can do it one more time. And you can see this moving down and the clouds forming over the Great Lakes there. And so just kind of a quick animation, but then on a broader scale, here's this Arctic air mass, continental Arctic air mass moving from north to south, but then over here to our west is some sort of likely polar maritime air mass coming. This where my cursor is like British Columbia and Washington State, and so you can kind of see this animation moving. So this is the other air mass now, and here's the separation of the boundary between the two of them. So as a reference, then likely a maritime polar air mass coming in from the west, and then it was interacting here with this Arctic, continental Arctic air mass. All right, so then that boundary between these differing air masses is known as a front, and we're largely going to focus on three major type of fronts, and even more emphasize warm fronts and cold fronts here right away. Note that there are more or additional types of fronts, but at least here for GC 100, we're really just going to focus on these three frontal uplift mechanisms. And so to tie back to some previous lecture topic covering like convective uplift and orographic uplift, and now here frontal uplift. It's where two air masses collide, and one of those air masses is going to go up and one is going to stay near the ground. And before we get to that, then let's just kind of go back also to refresh some of our or review some of our previous content. So was cold air more dense or less dense than warm air? Well, cold air is more dense than warm air. Again, warm air having more kinetic energy, energy of motion, and the molecules bouncing and literally creating more space, meaning there's less molecules per unit volume. And so if you have two air masses, one's colder and one's warmer, less dense, which one do you think is going to stay near the ground? The one that is more dense or the one that is less dense? Well, it is always going to be the air mass that is more dense. The colder air mass always stays near the ground. And so now we're going to separate this into two types of fronts. And so what this can look like on a continental scale is that a relatively warm air mass is advancing across the continent, and it has a lot of momentum, so to speak, and it's literally displacing a cold air mass that's in front of it or otherwise colliding with it. And so when a warm air mass is largely overtaking a cold air mass, that cold air mass is going to stay near the ground, and the warm air mass is actually just going to ramp right up over top of that cold air mass. The reverse then, or at least in terms of a cold front, this is when there's a really strong, powerful cold air mass moving across the continent with lots of momentum, and it's overtaking a warmer air mass out in front of it. And so when that happens, you have a warm air mass, and now this cold air mass coming in with a lot of momentum, so to speak. And what's going to happen is that cold air mass is actually going to stay on the ground, and the warm air mass is going to get pushed up really rapidly. And so in this case, warm air rapidly rises when a cold air mass is advancing. So let's look at that in more detail here. And so a cold front, again, this is the blue, the boundary is the front, and that's where a cold air mass is moving, in this case, from left to right, and it's literally moving rapidly with momentum, if you will, and it's displacing this warm air that's out in front of it. And when that happens, the warm air that's here near my cursor is going to get rapidly lifted, and it's going to go up. And so now, tying some of our previous content, whenever air masses rise, they expand because there's less pressure, and they cool. And when they cool, cold air can hold less moisture than warm air. Clouds form, and it may even start raining. And in this case, when we have a cold front with cold air advancing, you have rapid uplift, which means you can create lots of clouds and lots of rain. And so often with a cold front, you expect heavy precipitation to occur behind the front. Meaning, so now what I like to do is kind of like put myself on the ground. So this blue line, like over time, if you were going to track this as an animation, the blue line is moving from left to right, and it's right here, and it's going to keep moving, which means this whole cold air mass is moving this way. If you were standing right here, then you're in this relatively warm air mass on the ground, and then shortly that cold air mass is going to move over top of you. And so now as that cold air mass advances, all of a sudden the cold front has passed you, and then some period of time very quickly shortly thereafter, you're going to expect heavy precipitation. And so the keys here are heavy precipitation occurring behind the cold front. And so often in like a summer thunderstorm, for example, you can even feel this. I've felt it, and maybe some of you have also felt it, and if not, maybe pay attention because it definitely happens, and it's a common occurrence where you're sitting there. It's like this beautiful sunny day, and maybe you're sitting in a lawn chair at the beach or something, and then all of a sudden you get boom, you gotta get hit with this cold air, and like a stark breeze just kind of comes out of nowhere, so to speak. And so if that happens, it's not always the case, but if that happens, you might want to look up and look around. And if you see a bunch of clouds in the sky and you've just been kind of overtaken by all the abruptly cooler or colder air, you likely have just experienced a cold front passing over you. It went from warm to cold, and pretty darn soon it's likely going to start raining, and it's probably going to start raining heavily. So let's now flip around and think about warm fronts. And so in this case here, it's a warm air mass moving more rapidly with momentum again, kind of so to speak. But that warm air mass, more importantly, is overtaking a cold air mass out in front of it. And so now when a warm air mass is moving from left to right, always the cold air mass stays near the ground because it is denser. The warm air will rise, but when this happens, there's much more gradual rising. And so that warm air mass slowly ramps up over top of the cold air mass. And so one kind of unique and cool thing that I like to appreciate, which is much different than the cold front, is now put yourself on the ground surface here, and you could be kind of where my cursor is. And at the ground, you're still in the cold air mass. But then when you look straight up, you're at above you, literally thousands of feet, likely somewhere up there where the clouds are. That is where that warm air mass is ramping up over top of you. And what happens, again, similarly, the same adiabatic process, right? You have air rising, it's cooling, it reaches dew point, clouds form, and it starts raining. But again, in this case, because it's ramping up over top, now where my cursor is, you're still in that cold air mass, but that warm air mass ramping up over top of you has created clouds, condensation, and precipitation. And so now it's raining. It's likely kind of slight to moderate. It's typically not intense. And so you have more of a moderate, slow, steady rain, and it's raining ahead of the advancing warm front. So again, here's the warm front, the warm air mass advancing over top of the cold air mass, and now here is that position of rain relative to the advancing front from left to right. So the last type of front that we'll talk about in GC100 here, and this is a stationary front, and this actually relates to our convergent uplift, our last mechanism of uplift that we'll consider here in this course. And so what that looks like is literally you have two air masses, one relatively cold and one relatively warm, and they're coming and colliding, and they're really kind of going head to head and moving directly at one another, and they have about the same kind of momentum, if you will, where neither one's really budging. It's kind of the opposite of an evenly matched tug of war, or an even tug of war match rather, where like tug of war is pulling, but in this case you're pushing, and so you're just pushing against each other, and these two warm and cold air masses are pushing against each other. The front remains stationary. It literally doesn't really move because they're colliding, but there's still all of this air like literally moving in, and the air has to go somewhere, and it's not going to go down into the ground, so it's going to go straight up. And so right at that stationary front, you expect lots of clouds and rain to occur. And so here, a stationary front is our example of a convergent uplift mechanism. So now let's turn our attention to mid-latitude cyclones. And so this largely, at least really all year, but especially in the summer, classic kind of like warm, cold, and then thunderstorm. And so let's learn a little bit more about how a wave cyclone is formed, and then what kind of weather conditions you expect relative to your position to these warm and cold fronts. And so simply, let's just think about a cyclone first. A cyclone is a mass of moving air or mass of air moving in a spiral. So let's just think we got this mass of air, and it's spiraling, but it's also moving as a spiral. A mid-latitude cyclone then is a well-organized, and tying to previous content, it is the center of that cyclone is a low pressure center or low pressure system, and it occurs in the mid-latitudes. And so it's a cyclone, a spinning mass of air with a low pressure center at the middle, and it's now migrating across the mid-latitudes. And for us, then it's migrating from west to east. And this is a real image, and actually the weather map to correspond to this image, then showing the low pressure center, and then you have higher pressures as you move out and away, and this very well organized system of a low pressure center with a distinct warm front and a distinct cold front, and they both then connect at that low pressure center. And so we're going to learn more about what kind of conditions you expect to occur ahead of the warm front, behind the warm front, then conversely, or kind of comparatively rather, the ahead of your cold front, and then now behind the cold front. I wanted to include this time-lapse image just to kind of like appreciate the cyclonic pattern. Here is an image and a weather map to correspond to that. And then here is another animation I found from this Colorado source that just kind of shows this cyclonic mass of air moving. And this is actually the eastern US. And so this is the Atlantic. And so this was a mid-latitude cyclone that had moved across the continent, and then the time and place of this, it's now moving and it's keeping moving, and it's just going to kind of keep moving out and away to the east. All right, so this now also really interconnects with our polar jet stream. And so tying to some previous content, thinking about polar fronts, the boundary between a polar air mass and a mid-latitude air mass, and that jet stream, often and quite literally, what happens is a low pressure center develops somewhere in the Pacific, and then once organized as this low pressure system, that low pressure center literally starts migrating with the polar jet stream. And so the polar jet stream is literally controlling both the speed at which it moves across our continent, but also the relative position. And so when there are these large dips or undulations known as Rossby waves, we will expect this low pressure center then to migrate down and along that path. And so it's kind of like along for the ride with the polar jet stream, if you will. We're going to further kind of expand and focus on this figure momentarily, which has a lot of really useful information embedded in what I think is actually a pretty simple graphic, considering how much information we can interpret from this one diagram. So I'll kind of leave it at that for now, but we'll come back to that in just a little bit. And so here again, we have this well-organized low pressure center with a definitive warm front, meaning there's warm air mass moving and overtaking a cooler air mass out front. And then connected to that low pressure center is also a well-organized cold front where you have a cold air mass moving and overtaking this warmer air mass out in front. And so again, it forms this low pressure center that's often can dip down across the Midwestern and even Southern US along these big dips of the polar jet stream, and you're creating frontal uplift. And so there's both warm front and cold front frontal uplift occurring connected to the spinning cyclonic mass. And so let's look at this graphic in a little more detail, and it really connects back to those. And I'm going to go back just a handful of slides to kind of show you can use this figure, warm front, as well as this figure, cold front, and now really what we're going to do is like re-express the same information, but on a planar, so like top down. We're going to look at it from top down instead of from the side as these figures are showing. So now let's flash forward. Sorry for the clicking. And now what does this look like? So when we have a warm front, we have relatively warm air moving and overtaking relatively cold air out front of it. And then these key take-homes of a warm front include warm air that's going to ramp up and over top of the cold air in front of it. And when that happens, you have air cooling as it's rising. It's then condensing, clouds form, and it rains. Here, our blue diagram. It's going to rain in front of the warm front, and that rain is going to be light to moderate and relatively steady. And so you'll have this kind of like long, steady periods of light to moderate rain. All right, and so now then to focus on our cold front, we have a relatively cold air mass. And so again, this is a cyclonic system. You can see these arrows in the wind directions literally corresponding to these arrows. It's a cyclonic system, and this air mass now is colder air moving, and it's going to move and overtake the warmer air out front of it. And so when that happens, again, the cold air stays at the surface, the warm air rapidly rises up above the cold air. And when that happens, clouds, because the air is rising, it's cooling, it condenses, clouds form, and rain falls. And now rain is falling behind the cold front. So this is the advancing cold front, these blue arrows indicating the direction of movement. And similarly, the red half circles indicating the direction of movement here from lower left to upper right. And so here it's going to rain behind the cold front, and we're going to expect that rain to be intense. The last thing I want to point, and I did mention it once, but I just kind of want to emphasize these arrows are really useful. You can really largely expect the wind direction relative to your position of the warm front and the cold front. So if you're here in the warm air mass, you're likely in clear, relatively clear, sunny, warm conditions, and the air is moving from the southeast, and so southeast wind direction to the north, or sorry, south. Oh, I correct myself. Oof. These arrows are moving from the southwest, so southwest wind direction, and then they're moving to the northeast. I apologize. And so here, really, you can just kind of follow the arrows. Here, in this case, the wind direction coming from the southeast. This arrow would be from the northeast, this arrow indicating from the northwest. And so all of these arrows indicating wind directions, which is also really useful. All right, so now this evolution. And so again, you have this organized low pressure system developing over the Pacific. It's being kind of dragged across the continent, so to speak, by polar air and by that polar front or the polar jet stream. So you have this organized low pressure center. And so now the temperature is decreasing behind the cold front. You have these changing wind directions. So this organized cold front, again, your wind direction, and to reiterate then, our wind directions coming from the southwest, moving to the northeast, and then behind it, you have air moving really from the northwest, and so northwest wind direction. And so you have this direct wind direction change and this intense thin band of precipitation occurring behind the cold front. The warm front is where it's often moving to the north and to the east, the warm front itself. And so here you have warm air ramping up over top of cooler air out front. And when that happens, you have cooler air, the warm front passes you, and all of a sudden it gets a little warmer or considerably warmer. And typically you have this kind of broad band of precipitation that's occurring ahead of that warm front. And so for activities and exercises that accompany this lecture topic, these 4 diagrams tying back to our previous lecture topic and our current lecture topic here are really quite useful. And so to slowly kind of work our way through, here again, high pressure systems, you have descending and diverging air, and it's moving in a cyclonic pattern as well, so spiraling. And so high pressure is when air is coming down toward the surface from up in our atmosphere. It's hitting the surface and going out and away in all directions, where really the focus so far of today's lecture has been these low pressure centers. And so the low pressure center is where air is rising, ascending. And so when air rises or ascends, the air at the surface is coming in or converging. And literally, it's like making up the fact that that air is being pulled up or sucked upwards. And so at a low pressure center, you have air converging and rising. And then often within the scope of a continental scale, you have this balance of a high pressure center somewhere on the continent here. So air descending and diverging away. And so now you could kind of just put this component of this diagram right over top of that high pressure center, where you could expect wind directions to be going out and away from that high pressure center in all directions. And then similarly, you could kind of put this portion of the figure right over that low pressure center where you expect converging winds, and they're cycling around and they're ultimately then rising literally right at that low pressure center. Air is ascending in that place. And then we just went through this graphic. And so here you can use all of these graphics to kind of expect or predict where it will be raining or not raining, where it'll be sunny, where there'll be moderate or light precipitation, where there'll be intense precipitation. Is it relatively warm? Is it relatively cold? And so with that, we will continue here to move on. But these are four very useful figures interpreting wind, temperature, and precipitation on Earth's surface. So let's talk a little bit about thunderstorms. Those are pretty cool. And so let's think about it. And so here especially with advancing cold fronts, we have these air parcels that are rising. And as they rise, they condense and clouds form. And so as they continue to rise, those clouds then are being like literally developing and being extended upwards. And so this developing stage, and so you have the air parcel rising, it condenses, and we often form what we call cumulus clouds. And then cumulus clouds start to develop and they get extended upwards as that air is continued to be forced upward based or because of these frontal uplift mechanisms, and at which case then it extends far enough to be called what's a cumulonimbus cloud, which is your mature stage of a thunderstorm. And the one thing that I really like to appreciate about these cumulonimbus clouds, they go from smaller cumulus clouds that are what I call Simpsons clouds, like the classic cartoon cloud. They start to get a little bit bigger, literally taller. They're extending up in the troposphere. And then when they reach this mature stage of a thunderstorm, you have cumulus clouds that now have extended, and they're literally occupying sometimes tens of thousands of feet vertically that singular thunderstorm cloud or system of clouds into our troposphere, and they can reach these heights of like 30 to 40,000 feet. And literally what's happening is they're extending all the way to the top of the troposphere, where you reach the tropopause and the boundary to the stratosphere. And there's this incredibly sheer difference in what happens there when it reaches that boundary. That thunderstorm cloud gets dragged, and it kind of has this like anvil shape. And so perhaps you have seen that on the horizon when they're in the summer, especially with thunderstorms, these giant clouds with this kind of tail. And whenever you see that tail, that literally is because that cloud has reached the top of the troposphere and it's being sheared off by that tropopause boundary. Within your cloud, it's kind of cool. There's both updraft and downdraft within that large mature stage thunderstorm. And that's where you can have this intense precipitation downpouring and actually being like pushed down by the downdraft even further. And so in the mature stage, you have both vertical and so vertical upward and then vertical downward movement, which creates a lot of friction. Talking about lightning next. But then at the dissipation stage, as that mature thunderstorm starts to dissipate, you really just have a complete like downpour and downdraft where there's very little to no updraft within that thunderstorm any longer. This is where there's incredible amounts of rain. There's still a lot of rain here, but it's really just kind of releasing all of that moisture at that dissipation stage. And so getting to lightning, really, I mean, thinking about this mechanism and the fact that every water droplet has a nuclei, which is a particulate, and then all of these molecules and all of that friction can generate this incredible amount of electrical energy. And so within the cloud, there is a positive and negative like region of the cloud. And so typically at the base of the cloud, you have this incredible buildup of negative electrical energy. And at the surface, we have this positive energy. And our lightning forms when our leader comes down, and that negative leader is then going to meet up with the positive lightning. And so when we see that, it actually often is there's like a meeting of a electrical charge coming from the cloud, the leader downward negatively, and then here your positive streamer moving up from the highest point, which can be a tree like this figure, and it's really just all this collected positive energy from the ground then being funneled through the tree, and they meet and spark. And even often when that happens, you have like many leaders and streamers connecting like almost instantaneously, very rapidly in sequence. And so voila, we have lightning. Pretty cool. So a little bit about tornadoes now. And so what are tornadoes? We have small, intense cyclones formed in these supercells, these incredibly mature thunderstorms. And so this happens especially when you have these air masses moving from continental and marine locations, and they're coming in and they really like are battling each other, and you're creating a wind shear. And so in these frontal systems, as we've been focusing on, just appreciate you have two major air masses coming from two very different places around the world, like literally these air masses. Now they're colliding at these kind of sharp angles, and they're really creating this shearing effect. And so not only do you have this frontal uplift, but now you have two air masses perhaps kind of covering or crossing each other, and you're actually now creating some horizontal spinning because of those air masses as they're coming across the continent interacting. And so this is kind of your step one stage for developing a tornado, is to create this kind of spinning axis of this horizontal spinning air. Within that convective uplift, now literally you have updraft or uplifted air. And so literally as that convective updraft occurs, you're going to take this horizontally spinning air and start to like invert it vertically and contort it, if you will. And then finally you've like literally vertically assembled the spinning air, and now you have this like vertical spinning stack of air. And so I will encourage you here to pause the lecture and watch this very brief 3D visualization of the anatomy of a tornado. Check it out. It's pretty cool. It really kind of ties this together with some really sophisticated graphics that are beyond my capacity. So Tornado Alley, what is it? And so going really back to the first slide of this lecture, thinking about those air masses as they interact, most of those air masses are really kind of like interacting somewhere here. And so we have these tropical maritime or tropical continental, and then we have Arctic, and we have polar maritime, and they're all kind of meeting up somewhere around here, which creates strong frontal uplift mechanisms. And so now we have lots of uplift, and then it's also creating that wind shear to create those horizontal vortices, which then is our recipe for creating a tornado. And so because they typically meet up right around here, and it is pretty darn warm in the summer in this region, you have also just lots of convective uplift. And so now here producing Tornado Alley, which the majority of our thunderstorms occurring in this region, and you can kind of see like average per year counts of tornadoes. And so thinking like 45, 50, even Texas being pretty large, but 136, but then tapering off 21, 20, 18 in Michigan. And so we'll still potentially receive tornadoes in Michigan. And really, there's only few ever documented in the UP. They do occur, but they are very infrequent. But then compared to places like Iowa, and Texas and beyond here, all through the central Oklahoma region, and being born in Iowa, I've seen a couple pretty intense thunderstorms, including one tornado with my visible eyes when I was a kid. I could digress, but let's keep going because thunderstorms and tornadoes are cool, but hurricanes and tropical cyclones are also really interesting. So let's check them out. And so a hurricane is a tropical cyclone, which is a tropical storm that originates, or for us, a hurricane originates in the Atlantic or Eastern Pacific, and then tropical cyclones, and then also known as typhoons and simply cyclones in other portions of the world. Really, they're all created with the same recipe, just in different regions. And so let's kind of like examine the development of a tropical cyclone. And because here we're in the Northern Hemisphere in North America, as we refer to them here as hurricanes. So how does it work? So first recipe or ingredient, so to speak, is warm ocean surface temperatures. And so near the equator and in the subtropics, we have very warm near surface ocean temperature conditions, which produce incredible amounts of evaporation. So now we're adding tons of moisture into the atmosphere, and you have lots of convective uplift. And so you have this favorable upper air winds. And then when these larger air masses, as we've described, are moving across on continental scales, moving with the trade winds and with these global circulation patterns, you can create these conditions where you actually have high pressure aloft. And so high pressure, then you have this descending air mechanism. And so when you combine all of these factors, you're creating a spinning environment, but kind of like a thunderstorm, but very different in this case. You have both updraft and downdrafts occurring within a hurricane, and you need kind of all of these conditions to produce this cyclonic pattern that also has updraft and downdraft kind of co-occurring in a relatively short space. So let's check that out. So there's this eye of a hurricane, and so you can see these are kind of time-lapse images of a hurricane. So there's the center, the eye of a hurricane. Oops. And within the eye of the hurricane is that high pressure descending air. And so you have this descending air at the center. And actually in the center, it's quite mild relatively compared to that eye wall. And within the storm is really the most intense portion. The highest winds are right at the edge on this eye wall. But within the eye itself, it's literally like clear and relatively calm. And so here, then you have downdrafting or this air descending, and then at the eye wall and surrounding the cyclonic pattern, you have this massive amount of updraft, this convective updraft, and then again organized into a cyclone. So with that, this next click to watch flying through a hurricane eye wall, like literally this title, perhaps, and it is most definitely one of my all-time favorite YouTube videos. So check it out. Click to watch. Let's watch some really adventurous scientists literally fly through an eye wall to get some really good data. All right, coming back. Hope you enjoyed that YouTube video, one of my all-time favorites. So let's kind of keep going, exploring the geography of tropical cyclones. And so there's this peak season kind of from early or summer through fall, which is our most intense heating period. Again, hurricanes being in the northern hemisphere here. And so the highest occurrence of hurricanes is during this peak season, during this official hurricane season, where the peak season really is kind of a little sooner than the end of November and a little later. And so from August till October is this peak season when most of the hurricanes are occurring. To show many of the tracks of previous hurricanes and some more famous ones like Katrina, these hurricanes can take incredibly different paths. And so they're originating again by that warm ocean water near the surface, near West Africa, and the trade winds that are in that place on Earth are actually pushing from east to west. And so now you're moving in this evaporation, and you have the high pressure aloft, and you create a tropical cyclone, which then can strengthen into a hurricane, and it keeps moving across. And depending on those, all of the air masses and how that weather, they can take a very much more west to east path and end up within the Gulf here. And hurricanes like Katrina then affecting landfall here across the Gulf in Louisiana, Texas, and Florida. However, other hurricanes, and then really the Caribbean being always and quite affected by many and most of these tropical systems, not all of them, but as you can see, all of the Caribbean here, this whole region experiencing lots of hurricanes. And so other systems can kind of get deflected and then perhaps not necessarily the eye never makes landfall, although there's definitely weather, but then they get sent up across and up the northeastern seaboard, and some of them even making landfall in the Carolinas. And so we'll kind of come back and examine a couple of those systems later. I just wanted to show another one of these animation loops here of Hurricane Melissa. And so this was one of the most powerful hurricanes ever recorded. And so this is this time-lapse image of it passing through the Caribbean. So let's check it out. So you can see as it strengthens, this eye wall is really definitive. As it's moving over the ocean, it has this really strong and well-defined eye wall. And then as you see, as it hits land, the eye wall even disappears kind of, and kind of comes back and disappears. And so that warm water with that evaporation and convective uplift and that incredible amount of moisture is really what's like driving these hurricane systems. And they're still incredibly strong storms as they reach and pass overland, but then as they pass overland, they weaken in strength. And so actually, depending on storm tracks, and just to kind of show you some of these storm tracks like Rita, they come up into the Midwest. And so often when there are these large hurricanes reaching landfall in the US, depending on their direction and trajectory, even us all the way up in Michigan will receive some of that moisture that was originated way over in West Africa as rainfall. A couple last thoughts about hurricanes. One is there's this really kind of cool or also devastating condition called the perfect storm, which was a movie here. I believe Tom Hanks featured in that one, but it was based upon a true perfect storm from 1991. And so here's some old satellite image of that perfect storm that you should here click to watch to understand the anatomy or of a perfect storm. So what this perfect storm and perfect storms look like are when a hurricane interacts with a strong mid-latitude cyclone, and literally somewhere near the eastern US, typically those two systems are like collide and combine, and they produce these incredible conditions that can be incredibly devastating. And so here, the perfect storm in 1991 was when a hurricane interacted with a mid-latitude cyclone. And actually another system, and Hurricane Sandy in and of itself was a very powerful, or really just more broad. It didn't have the strongest winds when compared to hurricanes like Katrina, but it was this massive in space. But Hurricane Sandy also met up with, so to speak, or combined forces with the mid-latitude cyclone in its kind of like path. And when that happened, what even more flooding and damage occur. And so as you're likely aware, or as we pay attention every year, especially during hurricane season, you hear of hurricanes making landfall. And so that then really like literally translates into loss of life and loss of property and this incredible like economic impact, some larger than others. And so with that, I'll leave you of this really quite peaceful and pleasant view of Hurricane Florence way back in 2018, but just a really nice image of that hurricane eye wall. So With that, Dr. VG is signing off.